Okay, now that we've got your attention, because we're changing pictures, I'd like to welcome everybody to our July open night. Your guest, usual host, Frank Summers, is on travel. That means you'll get home early enough to let the cat out tonight. Just teasing. And there won't be a quiz after the talk. My name is Ray Villard. I'm the news director here at the Space Telescope Institute. We've got a fascinating talk tonight dealing with our cosmic origins, the origin of the solar system and the planets. Frank usually gives you the big Hubble news rundown. I have the Reader's Digest version. And I'm going to show you one item, and I wanted to show you this tonight because it dovetails with what our guest will be talking about. But the news just came out today, so you may not have heard about it. So I'm not going to give you a quiz, but who can tell me what spacecraft is that?
Apollo?
No, you're off by 40 years. No, you're off by 50 years. Nobody. Okay. No, but you're getting warmer, or should I say colder. Come on, you guys paid $1 billion for this spacecraft. You should keep track of, well, you're getting colder. You should keep track of where your money goes. Yes.
Voyager.
Not Voyager, that's way the hell out. And I don't think it's beyond the edge of the solar system. That's my personal opinion.
Break your heart and tell us.
Okay, I will, because time's going. This is the New Horizons craft headed for Pluto. It is controlled here at the Applied Physics Lab down outside of Columbia. And this craft was launched 10 years ago. It is the fastest man-made object ever built. And this is its trajectory as of today. It is a marathon runner. It has sprinted across the orbits of all the major planets. It is a year from flying by the planet Pluto. And with Frank not here, I can say planet. Pluto actually is a dwarf binary planet. An interesting idea, which gets lost in all the silly fight over the semantics of what to call it. Whatever Pluto is, it's very interesting. It will reach Pluto in July, but the people running New Horizons would like to go farther. They'd like to boldly go even deeper into the solar system. So the outer rim of the solar system is a vast undiscovered country stretching from 3 billion to 5 billion miles from the sun. It contains primordial debris going back to the birth of our solar system 4.6 billion years ago. We've never been there. And we've only known about objects out there since the 1990s. The folks on the New Horizons probe, after they fly by Pluto, wanted to visit a Kuiper Belt object. These are objects that range in a variety of sizes. Typically, the one they want to fly by is about the size of Manhattan Island. But we have to find it, and only Hubble, not any ground-based telescope, has the ability to look for targets for the New Horizons probe. So just released today are pictures of 2 Kuiper Belt objects. These are extraordinarily faint. They're about as faint as the glow of a flashlight on the moon, if you could see it from Earth. Now, how do we know that these are Kuiper Belt objects? Because God put little green circles around them. Stop it. God put, these 2 objects are 4 billion miles from the sun. Well, how do we know they belong in the Kuiper Belt? Because they're moving against the background of stars. That background is in the summer constellation Sagittarius. So finding these was like playing a game of Where's Waldo. It was a needle in a haystack search. We announced today that we found 2 of them. This means that more than 140 Hubble orbits will be dedicated to looking for more Kuiper Belt objects, which would be suitable targets for New Horizons. So probably by the year 2020, if that team finds a suitable Kuiper Belt object, it will fly by that object, and this will complete mankind's initial reconnaissance of the solar system, going back to the early 60s, because these Kuiper Belt objects are the last class of object in the solar system. We will have completed the chapter of our initial exploration of that. Yes?
You said if you find this, you'll fly by it.
Yes.
Does that imply that you are able to direct?
Yes.
Wow.
Yeah, wow is right. No. If Hubble the Hubble survey finds an ideal target, the New Horizons will be redirected after it passes Pluto to fly by this object. Again, finding these is like trying to find, I said Manhattan Island, but imagine Manhattan Island covered in black velvet, 4 billion miles away. And Hubble found it, the almighty Hubble.
What about the Oort cloud?
No, well, Oort clouds are light year away. So unless you invent immortality, it's not going. I don't want to digress, but the Voyager spacecraft that's on the way out, it'll take it, I think, 10,000 years to reach the Oort cloud. So again, that's about 50,000 astronomical units. Kuiper Belt is no more than 5 astronomical units. Now, I wanted to bring this up because the talk tonight deals with disks around other stars where planets are forming. So this is a Hubble picture, and nobody dropped ink on it. They just blocked out the star. But this is a Kuiper Belt-like disk around another star. And it's really evidence, circumstantial evidence, for the formation of planets around other stars. And that's really the talk tonight. And I think these disks are important. They've only been known about for about 15 years or so. If you ask a child where did they come from, they'll say the hospital. But studying the Kuiper Belt disks go back to 4.6 billion years. Where did the solar system come from? So we have a wonderfully enthusiastic speaker tonight, Andrea Banzatti, who has specialized in the chemistry and physics of how planets form inside these circumstellar disks. He's a postdoctoral fellow here at the Space Telescope Institute now. He got his PhD from the Institute for Technology in Zurich, Switzerland. I hope I got the name of that right, or close. Zurich Institute for Technology in Astronomy. He got his master's working at the European Southern Observatory's headquarters in Garching, Germany. And he got his master's and bachelor's in Italy. With that, please welcome Dr. Banzatti, who's going to tell us all about Oh, there's another Kuiper Belt. I see one. Kuiper Belt object.
You hear me?
Not very loud.
No.
I don't know.
Yes, it's on. Experimental physics. It's on. Hi. Hello. Hello. You hear me? Okay. So I have different instruments here. I think I need only this one for now. So Frank is not here tonight, but actually he's the inventor of the name. He made up the title for this talk, Building New Worlds in Protoplanetary Disks. I simply told him that I was working in plan information, and he came up with this appealing title. And when he told me this title, I felt a bit of vertigo, because this is much broader than what I actually do in my research. And at some point I was even, you don't hear?
It needs to be louder.
Louder.
Wait, that works. Is there a volume control?
Closer than this, I think I cannot go until I put it in my mouth.
Yeah.
Do you hear me?
Yes.
I will shout. How about that?
Yeah. Okay, that's better. Good.
I can shout. Okay? Okay? Okay. 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 So I was saying that I was tempted. So Frank made up the title for this talk, and I was tempted at some point even to change it and to narrow it down on a couple of things on which I'm working on in details. But in the end, I decided to keep the challenge and keep the title for one reason, mainly. I thought about it, and for one reason, I decided to keep the title, as broad as it is. Because of the mystery I feel attracted to. I know that even with an entire life dedicated to working on plan information, I will not solve this mystery. And yet, I feel attracted to it. Like, for example, like Sherlock Holmes, who cannot stay away from intriguing facts that he reads on newspapers. Okay? And like Sherlock Holmes, I like to go on the crime scene to see what happened. Okay? In other words, I am an observer. I like to look at facts, collect hints, and try to see the story hidden beyond the appearance of things. I think that all of you understand the kind of investigative approach that I'm talking about, because this is not something for astronomers or for scientists only. Otherwise, you will not be here tonight. This is something that we discover in ourselves, at least at some point in life, at least when we are kids, okay? And in fact, astronomers are a kind of never-growing kids, okay? But what is the mystery that I'm talking about? So let's imagine for a moment that we are Sherlock Holmes. It's early in the morning, and after a delicate British breakfast, we are ready to read the daily newspapers, okay? And since we are experienced investigators, we know that the news written big in big capitals on the front page, they are the least reliable, the most contaminated, no? So as experienced investigators, we go and look for the news written small in a corner, those news that are dedicated a few paragraphs at the end of the newspaper, okay? The section that you would read only if you have a lot of spare time during the day, and we have it because we are Sherlock Holmes, we have nothing to do. So today, this morning, we open the newspaper, and we read a title written small catches our attention. A title that reads, "A story that begins in a breathtaking beauty and ends in an unexpected way." Unexpected. This is for us. So we immediately go to the section blah at the end of the newspaper, okay? And this is what we read. Let me see if, before reading. Okay. With increasing telescopic capabilities, it turned out that the interstellar space is not as black and empty as it looks to human eyes from Earth. Diffuse gas and dust are present everywhere in our galaxy, with tenuous emission that can be seen with modern large telescopes, like the NASA Hubble Space Telescope. These regions are primarily made of gas, 99% in mass, with only 1% in small dust grains. It is from the interplay of gas and dust and the surrounding radiation that amazing figures are carved deep into the interstellar space, providing undoubtedly some of the most beautiful images of the local universe. Driven by observational evidence, scientists propose that stars are formed by collapse of droplets of material in these regions. For reasons that are not yet fully understood, at some point, dense cores become gravitationally unstable and rapidly collapse in a flattened rotating disk, which in turn accretes material onto a forming star, a protostar at the center.
Slower, please, slower.
The reading, sorry. With time, disks disappear, and the newborn star is ready for its mature phases on the main sequence, burning heavier and heavier elements in its core, and eventually releasing them back into the interstellar space. But this is another story, and we shall not get distracted, as it is right now that we unexpectedly notice something that was not previously under focus. Scientists propose that this physics would let us believe that the circumstellar matter is quickly accreted onto the star or dispersed by high-energy radiation. And this has been largely confirmed by observations. But the circumstellar material does not completely disappear. Some spherical bodies, solid and gaseous, rotate in orbits flattened on a plane that resembles the initial disk. So, at the end of the star formation process, we find planets. The reader could gently remind us that this is not surprising, and that if that were not true, we would not be here concerned with these matters, nor with any other one. We would then gently remind the reader that it was only yesterday that planets have been found to be the natural outcome of star formation, and scientists are still struggling to find a comprehensive way to make this happen naturally in their models. This is why circumstellar disks are increasingly dedicated efforts in astronomical research today, to unveil what they secretly do inside themselves in order to build new worlds, and such a variety of worlds that can be so different from our own. A challenging task, if we consider that since the beginning, this field of research has been driven by observations and unexpected discoveries. But challenges and the unexpected are the two pillars of cutting-edge research and triggers for investigative minds. So let's now drop the Sherlock Holmes character and get back into myself, if I can distinguish the two. I don't know if I can. I chose this article to set the stage of the topic of tonight, of the mystery that we address tonight. How planets, and not only planets, but worlds, can form inside protoplanetary disks. And the crime scene that we need to go to are circumstellar disks or protoplanetary disks, like those that we see in this beautiful image of the Hubble from the Hubble Space Telescope. Here you see images, and there you see an artist's impression. And so the mystery we address tonight is a story that begins in a breathtaking beauty and ends in an unexpected way. So, as a first thing, let's look first at a couple of things to understand better what we read in the article. Okay? And let's start from where Sherlock Holmes would start, as well as any astronomer would start when we address a new unknown problem, the library. Okay? I remember my PhD supervisor used to tell me that when he started in astronomy some 25 years ago, he used to go, am I going to
Much too fast. Much too fast. I can
Too
barely
fast.
understand you.
So I still remember that my PhD supervisor told me that when he started in astronomy some 25 years ago, he used to go regularly to the library physically and be able to read all astronomy papers that were published worldwide. Okay. Now it's more difficult because something like 100 new papers come out in astronomy every day. So if you spend your time reading them, you spend your life reading them. But now we have a wonderful online tool, which is an online library, where we can search for papers, even back in history, using keywords. Okay? And this is what we are going to do now. Okay, so let's use two keywords using things that we have that were mentioned in the article: circumstellar disk and exoplanet. Okay, in this plot, you see the number of published papers in 4 slots of years over the last 35 years. Okay. Let's look at exoplanets. What happened at exoplanets? So these are papers that were published with exoplanet in the title. Okay? Sorry. But we are going to stay here for 2 hours if I don't... so I can slow a little bit down, but not too much. So this is what happened in the field of exoplanets. What do we see from here? That the interest in exoplanets has grown enormously over the last 20 years. Okay? Let's look now at circumstellar disks. This is what we find. Okay. So while we see that the interest in exoplanets has grown a lot, it seems that the number of publications, the interest in circumstellar disks is not really growing anymore. Actually, we can imagine from this we can conclude that the interest in circumstellar disks is going to die very soon, because exoplanets are the sexy thing now that we want to look at. Okay? And here is where an investigative mind is triggered. Because maybe we don't have the full evidence in front of us. Maybe we are asking the wrong question. You have heard in the title that here I'm talking about circumstellar disks, but they are now more known with the name protoplanetary okay? And this word was created to suggest the idea that planets are formed inside circumstellar disks. Okay, we are talking about the same thing, okay, but they are called either circumstellar or protoplanetary, okay? And this idea that planets are formed in circumstellar disks is much older than exoplanets, than the discoveries of exoplanets, okay? And was born by considering an interesting similarity between the orbits of the planets of our own solar system that are flattened on a plane, and the first images of circumstellar disks that were a disk, so flattened on a plane. So now let's look at papers, publications with protoplanetary disks. And this is what we find. So this is interesting because it's telling us one thing. Well, two things. First, we find what the article was saying. So indeed, the interest in protoplanetary disks is increasing and has been increasing a lot lately, okay, in the last 2 decades. And second thing is that exoplanets seems to be the driving force shifting the focus from the origin of stars in the word circumstellar to the origin of planets. No, we are talking about the same thing, but now instead of calling it circumstellar, we call it protoplanetary. Okay. So this strongly suggests, and you see that the rise of the protoplanetary name, the use of that name, is together with the exoplanets. Okay, but now let me ask you this question: if right now there is a huge interest in exoplanets, and if by now it's apparent, it's clear that exoplanets are common around other stars, why should we care how they form? No, they simply are. Why should we care to understand the details of how they form? And to address this question, let me bring you to the back in time, to the time when the curves here start to diverge, to the early 1990s. When the first exoplanets were found. Here you see the first 2 papers, 1992 and 1995, that were presenting the first exoplanet discoveries. Okay, and now to understand the key point of these 2 papers, I want to do an experiment with you, and I need 1 or 2 volunteers who feel like Dr. Watson and want to play with Sherlock Holmes. Come in. Even 2 people. 2 people is fine. Come. There is one test you have to pass to participate to this test, to this experiment. What is inside here?
Starch.
What is this?
It's starch.
Okay, you go and you stay. It's pasta, man, pasta. Anyway. Okay, you stay. What is it? It's pasta. Okay. No, you stay. You learned one important thing tonight, that this is pasta. So, the experiment I want to do is to, we have our star. This is, as you see, it's a star. And now we take the material of which the star is made, which is
Pasta.
and we put it in rings in a disk. Okay, as if. So we are using the same material to make the disk because the star is made from the disk. Okay, so I'm allowed to do that. Okay, so we use the material of which the star is made. Let's do it. You make 2 rings, one very close. So put it here, and the other one as far as you can to within the limits of this table. Let's do this one. Okay. So you do the small one, you do the large one. Doesn't matter if it's not super. Okay, and please pay attention because this is Barilla. It's not. So in the meantime, I have something also for the rest of the audience. You can try to guess my country of origin from.
China.
Close. A little bigger. Okay, great. So the rest, let's put it together, the inside. The rest we put inside. Okay. Good. Wait, we are not done. Come here. Okay. All right. Now, next step. I want you to form two planets at the two distances from the star that we have here, where we have material, okay, using only the material that we have at that radius, okay? So let's do that. Just exactly. All right. All right. Well, come on. I'm going to eat it afterwards. Okay, let's do something like that. Okay, let's assume that let's assume that planet formation works better than this, but the planets actually stick together and then okay. Now, in this kind of scenario, where would you form the most massive planet and where would you form the least massive planet?
The most massive would be at the farthest radius.
The farther radius. Why?
Because
You can answer too, because you have more
the
pasta.
It wouldn't necessarily, the largest planet wouldn't necessarily have to form closest or farthest.
Don't go too far. Come on. I make the questions. And you answer. Wait. Don't go too far. Let's go step by step. Okay. So if this were a scaled version of our solar system, where would you form Jupiter? Where would you form Mercury or Earth?
This would be Mercury by representation scale, and that would be Jupiter.
Wonderful. Now, push back. Now let's look at the 1995 paper. What did they find? They found the Jupiter-Mars companion well inside the orbit of Mercury. This was very unexpected. I can tell you that I had the pleasure, you stay here, the pleasure of two personal meetings with this guy here, Didier Quello. You see, it's from Switzerland. I did my PhD in Switzerland for a reason. Well, I met him there, and I heard from him the story, and the story of the discovery. And he has a wonderful story to tell about finding something unexpected, something that for the theories at that time was completely impossible. Was impossible, such that when they started to have the idea of what they were finding, especially Didier, who was a PhD student at the time, he was very young, he was worried because he said, this is not possible. It cannot be a Jupiter around the star so close to the star. It's impossible. Nobody would believe that because theories cannot explain that. Okay? But then it turned out to be true, and now we have many. No? Okay, let's go back to our experiment. Now, let's say that, okay, I orbited here and here, or here and there. Okay, so now let's say that at some point the star explodes in a supernova. What do you think would happen to the poor planets?
Well, the smaller one would be affected by this great explosion, so it would be moving out way up here due to the slow mass, so it would get accelerated more easily further. Whereas for this Jupiter-like planet, it would be already further out, so the explosion would affect it less. So it would be moving more like.
What do you think would happen? You are far too optimistic. This is what is going to happen. What What is this?
This is probably dust and particles.
Take one and go and don't step on it because it's body. So, I'm not done, but thank you for your help. You are really tricky. Anyway, so let's look now at the 1992 paper. What did they find? They found not one, but two planets were around a pulsar. A pulsar is the neutron star, the neutron remnant star after a supernova explosion. And even back then, those planets were found very close to the star. So you cannot say, well, optimistically, they are far enough out that they don't feel the supernova explosion. They were very close, inside the orbit of Earth. They would be destroyed for sure. So what is the point for which we made this experiment? I made it with you to make clear one thing, that since the very beginning, the field of exoplanet research has been the reign of the unexpected. Okay? And it is so even now. Let's look, for example, at this plot that is more recent. Okay, let's go to, this is 2013, where we see a representation of the population of planets, the exoplanets that have been detected so far. This is going to be difficult. Okay. Sorry. Okay. So even here, you see that the known population of exoplanets, we have a population here of planets that are more massive than Earth. This is the mass, and this is the period proportional to the distance from the star. Okay, so these planets here are more massive than Earth, but closer in, and these kind of they are called super Earths because they are more massive, and they seem to be really the rule in planet formation. It seems that every exoplanetary system has one. Okay, and we have a population also of Jupiters, which are called hot Jupiters, well, especially this one, that are closer in again than our Jupiter. Okay, here we have our Jupiter, here we have Venus and Earth. Okay, and this is just considering two properties of the planets: the mass and the distance from the star. Okay, many scientists say that when we will be able to study in more details the composition of the planets, of the atmospheres, and the bulk composition of the core, we will be very likely surprised by unexpected discoveries. At this point, we expect to be surprised by the unexpected in this field. Okay? So let me answer now the question: why should we care about protoplanetary disks? Why should we study them? Because we are surprised by the unexpected discoveries in the exoplanet field. And so we would like to understand how we can form such a variety of different exoplanets, as well as understand how our own planets and our own solar system can be formed. Okay? So let's now go step by step. What do we know about the planet formation process? And let's start simple. From the composition. Okay, let's look at the most familiar case, our solar system. We have the star, the sun, mostly made by hydrogen and helium, and the gas giants in our solar system as well, they are mostly made by hydrogen and helium. Okay, so our little experiment that we did here, it's a simplified version, okay, of planet formation, but our little experiment might have probably worked. Okay, we are using the same material to form big planets in the disk. Okay, but we have a problem. For these planets here, their composition instead is very dissimilar from the star. Okay, so if the disk had the same composition as the sun, these planets are peculiar because they are mainly solid, and they have a composition that is mostly made by compounds of iron, oxygen, silicon, and magnesium. Okay, in short, they are mainly solid. This is the evident, okay? Gas giants, solid, rocky planets. If you think that this approach is trivial to start from the bulk composition, okay? Well, actually, please consider that this is what we are still doing now with exoplanets. This is a very recent paper where we have the planet radius here and the planet mass on this axis, okay? And this one is a zoom in this portion of the plot. When we are able to measure the mass and the radius of an exoplanet, we can measure a mean density, no? Mass divided by the volume. And from the mean density, we can estimate a bulk composition, as if the planet was made by a single thing overall. Okay, so for example, we can see a planet made of water. The entire of water would lie on this curve, depending on the mass and the radius. Okay, only rock or only iron, etc., etc. Here we have, for example, in this paper they were presenting a discovery of one of the most Earth-like planets in terms of bulk composition. Okay. You see, the planets that they found is here, Earth and Venus, okay? And so it's the closest compared to other Kepler planets, okay? So, historically and classically, the problem of planet formation is a problem of solids. So, the problem to build bodies of at least a kilometer in size, starting from the dust grains that at the beginning of the story we said in the planet formation regions, in this nebula planet formation region that we observe, the size of these dust grains that we observe there is 1 micron or less, 10 to the minus 6 meters. Okay? So this is a jump of at least 9 orders of magnitude, okay, in size. We have to make this jump to build the planet. Okay? Think, for example, of going to the beach, and if you take a sand of grain, it's even more than the jump from that sand of grain and Earth, even more than that, because grains here are smaller than sand grains. So we are just at the beginning and already an unsolved mystery. Yes, because we know of thousands of exoplanets, but we still haven't figured out the details of how this jump happens, of this process happens, okay? What we know, however, is that at least the first step happens in protoplanetary disks, in circumstellar disks, because scientists have been able to measure the size of dust grains in these disks and found 1 millimeter, 1 centimeter, okay? So it's an increase of 3-4 orders of magnitude. And I've been working, when I was in Germany at ESO, I was working on this, in this field, measuring the size of the grains in protoplanetary disks. It's a first step. And yet, we still have to grow at least 6 orders of magnitude more. Good. So I said this is still an unsolved mystery in astronomy. But is it possible that, I mean, again, we know of so many exoplanets and we still don't know of this, which is like the fundament. If you cannot grow the solids, you cannot build planets. We still don't know because of two problems, mainly. The first problem is a problem of observations. While gas is mainly optically thin in these regions. Okay, this is the artist's impression of a protoplanetary disk, okay? So while gas is primarily optically thin, so we can see through it, dust is instead optically thick, so we cannot see inside the disk exactly where planets are formed, okay? To give you an analogy, imagine that you are driving in the fog and you are trying to guess if what you have in front of you is a car, a motorcycle, or a deer, okay? For the same reason, in protoplanetary disk, even though the small dust grains are small and planets that are forming there are possibly already big, the opacity is dominated by the small grains, and so we see only them, and we cannot see the big bodies, okay? And consider, in addition to that, that given the distance of these disks from Earth, they look to our eyes very small in the sky, like in these images from the Hubble Space Telescope, okay? And what we are trying to find, to see, forming planets inside them, are at most 100,000 times smaller than these blobs, okay? So no way, okay? But I said that the small dust grains, instead, we can measure, not the size. I said that the astronomers have been able to measure the size of the small dust grains for the same reason why the small dust grain, the small particles in the fog, they dominate in opacity, okay? And for example, with the VLA in New Mexico or the ALMA in Chile nowadays, we are able to measure the thermal emission from these small dust grains and measure and estimate their sizes. Okay, and find again that there is a step forward compared to the submicron grains in the nebula. Second problem we have, a problem of timescales. So while planet formation happens very, very quickly, it's very fast compared to the lifetime of a star, it's very slow compared to our lifetime, okay? So we would have to live 10,000 times an entire human life to be able to follow planet formation, a planet forming, okay, all the stages. So we have two ways out. When we cannot directly see what we are looking for, either we try to imagine it, making models, we try to imagine how that could happen, or we try to look at the same object but in different phases of evolution, okay? And then we try to connect the points and build a story, okay? And these two approaches, the theoretical approach and the observational approach, are both fundamental, and they sustain and help each other to build the story of planet formation, okay? Let's look, for example, at how theoretical models try to explain how we can grow dust in disks from the small sizes of 1 micron, as I said, 10 to the minus 6 meters, up to planet sizes of more than a kilometer, okay? This is from a recent review where a number of models are put together in order to explain how it may be possible to climb this ladder in sizes and go from dust to planets, okay? In the so-called core accretion scenario. So I cannot go into the details here, but this is to give you an idea that we have at least a few ideas on how, with following steps, okay, different processes, one after the other, or probably happening the same time in different radii in the disk. Again, we can go from dust to planets, okay. The first step, this one, number 1, that brings the dust from here to millimeter in sizes, is believed to be the one responsible for the emission that we see with interferometers, as I said before, okay. So the millimeter-sized grains that we measure that we detect in protoplanetary disks are probably formed by sticking of small particles. Okay. For the rest, the next steps are very much still unconstrained and mostly theoretical, and they are very difficult to constrain. A classical problem in this scenario is, for example, the so-called meter-sized barrier. In these models, it is expected that as soon as dust grains stick together and they grow in sizes enough and they reach the 1 meter in size as an order of magnitude at 1 AU, the distance of Earth from the Sun, they would start to feel a gas drag that would such that they would be sucked onto the star very quickly. Okay, so we have a problem of timescales here, because the material of which planets are made need to stay in the disk long enough for the planets to be made. Okay, if you suck all the material onto the star too quickly, nothing is left, no? And you cannot form the planets. But with these other mechanisms here, there is the hypothesis that there are overdensities of material in disks, okay, or the so-called dust traps that may allow to jump on the other side of this barrier, and once the planets, the solid bodies grow enough, okay, at some point gravity kicks in strongly, and so all the smaller bodies are accreted onto this planetesimal or protoplanet, and at some point also the gas participate to this flow, so that you can, it is expected that you can build a rocky planet with also a gaseous atmosphere, okay? And now, very recently, this is of the last few years, these dust traps start to be seen. So they may show us that indeed some of these models that propose these dust traps are really happening in this, so to allow to jump from one side to the other and then the buildup of planets, okay? For example, this observation is from ALMA. This is the location of the star. This would be the circumstellar disk, okay? They detected millimeter-sized grains only in this region, okay? Showing that these grains are not distributed on a disk as homogeneously, okay, as one would expect. But they are sort of trapped by some mechanism in that region. And these regions, called dust traps, are believed to be regions of efficient planet formation, because you bring solids on a smaller portion of the disk, and you increase the probability of interactions and the buildup of larger bodies. Okay. Now, so while this first step is observed, these intermediate steps may start to be observed, and we are starting to constrain them. At the very end, the final accretion of gas and material on the disk, on the protoplanet, is only very, very recently that we start to see also the last steps. And this is a very exciting observations that it was published in 2013. Actually, Sascha Quanz, he was a colleague of mine at the ETH in Zurich, in Switzerland. So what they showed here, this is a Hubble image of this protoplanetary disk. They started to detect kind of point-like, not exactly point-like, by small sources of emission inside the disk, still embedded, okay? And they interpret these observations as observing protoplanets where the disk material is still accreting onto it, okay? Onto the protoplanet. And these new observations are starting to connect the two ends of the story that until a couple of years ago were the only things we had. Circumstellar disks and exoplanets. Okay, in between, again, the story is still very unknown because we cannot see inside disks. It seems that we start, in some cases, to be able to see also the emission of some protoplanets. This is still a candidate, okay? It's not confirmed yet. But I believe that observations like this will increase in number in the near future. Okay, let's say that now we are able to overcome the problems and the barriers that are in our theoretical understanding, and we are able to form rocky balls in disks. Okay? Still, we don't have yet planets. Okay? So to do the next step from rocky balls, undefined rocky balls, to planets, let's address the composition in more details, okay? And let's look again at our solar system in this scaled representation, okay? One of the first things that struck me when I look at this representation is what you see immediately. So, gas giants out, rocky planets in, rocky planets small, gas giants big. There are solid bodies all over the solar system, okay? We heard even in the introduction, okay? All over, even in the outer regions. But as far as planets are concerned, the rocky planets are in, the gas giants are out. So there seems to be something there between the rocky and the giant. There seems to be a discontinuity. critical change between the inside and the outside. So the simple idea that this visualization seems to suggest was proposed in a paper in 1981, where, and here I'm showing the key figure, where we have the density of material in the disk and the distance from the sun, where an experiment similar to what we did here but reversed was done, which is to take the mass that is nowadays in the planet, okay, in our solar system planets, and spread it over rings of material, assuming that every planet contributes only to an annulus at its distance from the star, from the sun, okay? So to build a representation of what our own protoplanetary disk would probably, possibly have looked like, okay? And what he found is a discontinuity, okay? This is the density of material. And you see that if you connect the points here, you have a discontinuity between the rocky planets and the giant planets. And this discontinuity was, in that paper, attributed to a so-called snow line, which is the line marking the separation between regions where water is in the ice phase outside of this line, and in the gas phase inside, because of the temperature. Okay, when the temperature that decreases with the distance from the star drops enough, so to water to freeze out, then you have only ice on one side and gas on the other one. Okay, such that inside the snow line, only compounds and molecules more resistant to heat than water could survive. Okay, like silicates, for example, and so only rocky bodies were formed with the material, the solid material inside. Outside, instead, rock and ice would have allowed for larger, faster buildup of planetary cores, and then a faster accretion of gas to build the big gas atmospheres of the gas giants. Okay. Now, this simplified story that I just told is still very much assumed nowadays. Okay, and it has important implications on what we can learn about exoplanet composition by looking at protoplanetary disks. So let's look at the section of a protoplanetary disk. Okay, let's take it and let's take a section, the star, and here we cut the disk. Okay, and let's summarize in a cartoon the ingredients, the factors, the processes that we have talked so far. Okay, so we have the dust grains, small dust grains that grow in sizes. Okay, at some point that they grow enough to feel a gas drag, and they feel a gas drag and they migrate inward towards the star. At some point, because of some processes, they are stopped in their migration. Some of them are stopped, and they in this, for example, in these dust traps, okay, so that they can stay there long enough to build again in mass and reach the planetesimal size, the kilometer size, and then start to accrete also gaseous atmospheres. Okay, those grains that make it to the inside the water snow line that here has this strange shape because of the thermal temperature and density structure of the disk, which is more complicated than a simple line. Okay, inside we have ice evaporation. So for example, all water ice would evaporate and be in gas. Okay. So while the processes that happen in the planet formation region inside the disk are hidden to our eyes, we cannot see them, okay? We can observe the molecular gas in the inner disk through the infrared radiation of the gas, okay? And it is very recent, in the last years, that warm water and emission from molecules with carbon inside has been discovered in protoplanetary disk. And this is an achievement of another NASA telescope, the Spitzer Space Telescope. Okay, and here you see, here we use spectroscopy, infrared spectroscopy, to identify the molecules in the gas that produce the emission. Okay, we have here the observations and here a model. where you basically see that all the wiggles you see, well, the majority of the wiggles are due to water vapor, and these colored ones are due to molecules that contain carbon, okay? So this tells us that now we are able to trace some molecules, and not some irrelevant ones. We are talking about water and carbon-bearing molecules, okay? Back when they were in the disk, okay? And we can try to make a story to connect them to the composition of the exoplanets, okay? Let's see what we can do. One example of what we can do with these kind of observations. For example, let's take the composition of our Earth and the Sun, okay? And let's compare them. So the black line here is where all elements that we consider would lie. They would lie on this line if the composition of Earth and the Sun is exactly the same, okay? And we see that this is true for, I mean, many elements lie at least close to this line, okay? But some do not. For example, let me draw your attention to carbon that is underabundant on Earth, okay? If it is lower than the line, it means that it's underabundant on Earth by almost a factor 10,000, okay? If you think how much carbon is essential for life on Earth, you may be surprised by seeing how little carbon there is on Earth, okay? Now, this may find an explanation in the observations of protoplanetary disks, and in particular in the imprint that is given by snow lines in protoplanetary disks to the composition of exoplanets. Let's look at this plot from a paper in 2011. So far, I've talked only of one snow line, the water snow line, but actually, in protoplanetary disk, every molecule has its own snow line, which is the location in the disk. Okay, the star is here. We go further out. The temperature increases in these directions toward the star. Okay, so every molecule has its own snow line, where on one side, farther out from the star, it's in ice, only in ice form, in the ice form, and closer in is in the gas phase. Okay, so you have it, for example, water, CO2, CO. Okay, CO freezes at much lower temperatures than water, so the snow line of CO is much further out, okay, in the disk, and CO2 in between water and CO. So in this plot here, that is really a very interesting result from the last years, and even this one will grow in interest and in related papers in the next years for sure. We see that the composition of the gas, this line, and the solids, the solid grains in the disk, okay, this one line, the composition in terms of carbon abundance as compared to oxygen abundance, the number of carbon atoms compared to oxygen atoms, okay? The composition changes every time that there is a snow line, okay? Because in any given location of the disk, we have different contributions to the gas and to the solids depending on which molecules are in the gas phase or in the solid phase, okay? Such that we can imagine that if, depending on where an exoplanet forms in the disk, it will have a different composition, okay, depending on the location where it forms in the disk. And not only the planet, but also the planet atmosphere as compared to the planet's surface. In particular, we will have carbon-rich atmospheres for a large extent in radii, while we will have carbon-poor surfaces for a large range in radii. Okay, and this could explain a recent exotic example, the exoplanet WASP-12b, who was proposed to have, looking at its atmosphere, it's a hot Jupiter, this one. Looking at its atmosphere, it was proposed that the C to O ratio, the composition in terms of C and O, was close to 1. must be close to 1, okay? This was what was proposed. And this is very exotic, very strange compared to what we find in the solar system. This is the C2O, the composition of the sun, okay, in terms of C and O, okay? And an exoplanet like this could be explained if it formed in a location, in a comparable location in its own protoplanetary disk, okay? This could also explain maybe why Earth is carbon poor, okay, if it formed in a location of the our protoplanetary disk where carbon was primarily in the gas phase, not in the solid phase, for example, in CO. Okay? So this is where we are going now in this field. We are working on finding a link between the composition of protoplanetary disks and the composition of planets, exoplanets and planets that form inside protoplanetary disks, in an attempt to build a story, to build a scenario where we understand why and how certain kinds of planets can form in certain disks and why not others, for example. It's very early in this field, okay? Okay, and now we are at the end. So, we made it somehow to form a rocky ball in the disk. A rocky ball, let's say, even with an atmosphere. Okay? Second step, we addressed also the composition. So we don't have only a rocky ball, but we have something that we can call a planet. Okay? And we saw how the composition of the natal disk may imprint the composition of the exoplanet or the planet. But the talk tonight, the title says new worlds, not simply planets. Okay? And world suggests something more than simply a rocky ball with some composition floating into space. World suggests complexity, diversity, and life. So at the end of this talk, I have to at least mention an interesting symposium that we had just a couple of months ago here at Space Telescope in this room called Habitable Worlds Across Time and Space. We talked for days and we discussed for days about the details and many facets of this exciting topic. And that I was surprised that at the final discussion we found ourselves still addressing some fundamental questions. What is habitability? How can we define it for exoplanets? And how can we search for life beyond Earth? And all these questions are still very open. So, if the mystery we addressed tonight was not enough intriguing so far, the problem of habitability makes it a challenge that is and will drive research for many years to come, and also the interest of the public for sure. And no doubt that we will be surprised by unexpected discoveries. But as we read in the article, challenges and the unexpected are the two pillars of cutting-edge research and triggers for investigative minds. Thank you. I will need 2 volunteers to help me with the pasta.
So I like the pasta hypothesis. It's understandable. Anyway, we've got time for some questions. Please raise your hands. Available. Questions?
If you want to repeat the experiment, please.
You baffle them.
Well, okay, let me try one. The gas giant, Saturn, how does it get started? What's down inside that draws the gas in? After all, we have trouble keeping gas on Mars because it's too light.
So you're asking what's inside Saturn?
Yes, how does it get started? What's there?
So the idea is that you may, or rocky terrestrial planets in the inner disk closer to the star, and rocky cores for giant planets, if they have rocky cores. I don't think it's still super clear for our own giant planets, so it's not clear in general. But the idea is that even gas giants have a rocky core in them that may be the size of the rocky planets that we find in the disk, closer to the star. That they have at that location in the disk further out, if they build up enough mass, rocky mass, fast enough to form when there is still a lot of gas around, then, as I said, at some point gravity kicks in a lot, and so you accrete a lot of gas from the surrounding, from the ring of material, okay, at that location, okay. And so it's a problem also of timescales, how fast you can build up these cores, okay. So in the regions outside this simplified view of the snow line, being there ice other than rock, solid material, rock and ice, it's also seen from experiments that ice helps a lot in building up material because it's more sticky. There are a lot of experiments done with these little grains and try to see how they stick and if they stick or not, depending on the velocity. But it seems that ice helps a lot. Okay, so if outside of a snowline you can build up quickly a rocky core made of rock and ice, then you can accrete. Then there is at some point a runaway process that accretes gas onto it, and this is a way to explain gas giants. What is this?
Starch that has been turned into pasta.
Go ahead.
Has there ever been an exoplanet found that is a rock-based planet but yet reached the mass and size of a gas giant?
For sure. Everything you can think of is there, basically. So I cannot tell you a specific example. We can look it up afterwards if you want. But the message is that everything, nature is much more creative than us. So I'm sure we can find one. Within the uncertainties that we have now, I'm sure we can find one. There is really a large variety of planetary compositions and size and masses.
The universe is not stranger than we imagine, it's stranger than we can imagine.
That's right.
The moons of Saturn and Jupiter, are they considered mainly rocky, or are they mostly ice? I can't recall.
They are a mix. They are a mix. So some are very much ice, some are rocky with yeah. Actually, interestingly, in the plot that I showed, let me pull on this again here. This one here. Okay, unexpected. Okay. The green points, it's hidden, okay, because I wanted to make it simpler. But the green points are the satellites of gas giants. So there is an interesting overlap between the super-Earth's population and the gas giant satellite population. I know this is a bit aside of your question, but I wanted to just bring it up because there is this interesting similarity that may suggest of a similar process of formation. Not only having a similarity between the giant planet satellites, not only in our solar system, but in other, possibly in other exoplanetary system, and these super-Earths. And here the mass is scaled with the mass of the star, and for the giant planet satellites is scaled with the mass of the gas giant. Okay, so there is some story behind that, but there is this similarity, hinting at a possibly similar process. There first, I guess.
Here.
Yes.
So you might have mentioned this, but like you said, when they form, like was it 1 meter? They get, some of them get like sucked into the star in the middle.
The solid, yeah.
Like what exactly stops like all the planets that would have formed to be sucked into the star?
So what exactly, we don't know, okay? But we have two, again, we have the theoretical approach and the observational approach. Observationally, we have evidence for these clumps of millimeter-sized grains that are not homogeneously distributed in the disk but clumped in one region, okay? So that observation is telling us that there is some process that is keeping them there, okay? Even if we don't know what it is, okay? On the theoretical side, there have been a lot of creativity and imagination to try to explain that, okay? And so the idea is that there are these regions of overdensities in the disk, such that the density is not the same, okay? So these grains, while they, for example, one is the snow line, okay? The snow line is the region where you have on one side ice and the other side gas, okay? If you have a sharp region where on one side you have a lot of gas and the other side you have the same molecule, for example, water, but in solid, there is a discontinuity in density of gas material, okay? Because on one side you have a lot, on the other side you have less, okay? That would be a density region where dust grains could be stopped, okay? Even though some still make it through and produce the gas that is seen in the inner disk inner disk, because they evaporate, ices evaporate there, and then it's proposed that there is a rediffusion of gas outside, beyond the snow line again, building up again, freezing out water, for example, and building up again material, the solid bodies beyond the snow line. Okay, we don't have a clear idea. There are many complicated models to try to explain how you can stop these grains there. Okay, but we have evidence that happens. Okay, so we know that it happens. We still don't understand how. Yes.
Our article.
Oh, sorry, it's here first. Go ahead.
In your experiment, you showed that planets like Jupiter, so big ones, should form on the outer part of our solar system, stellar system. But why do hot Jupiters form next to the star, like the one we observe?
He will answer. You know the answer. You were saying the answer to his question.
The question was?
Okay. So I'm glad you raised it, because indeed here I showed two unexpected things, but I didn't explain them. Okay, and actually, well, one is still very mysterious. The one that you ask, the idea is that, and a lot of development has been done even at that time when these two Swiss guys were able to robustly demonstrate that there was a Jupiter mass companion so close to the star. From the theoretical side, they had to come up with something, okay, because they had to explain it in some way. And the idea was that the planet forms farther out in the disk, but then migrates in, okay? I talked about the migration of the small solids, but a similar migration may happen for protoplanets or planets, okay, by interaction with the gas again. So the idea to explain that, to explain the population of hot Jupiter, is that they migrate towards the star after they are formed. That's the... Sorry, back there, yes.
Particles at a given radius from any sun in this early formation time, are they all going at the same rate of speed, or do they go at different speeds?
I'm sorry, can you?
Do the particles go at, which might vary in terms of size, and composition, do they all go at the same speed at a given radius from some star, or do they go at different speeds?
It's an interesting point, yes. So they go at different speeds. When, for example, when the solid particles are still embedded in the gas, so when the disk is still in the early phases and you have gas and dust together, okay, at that point, when the particles, the solid particles, are small enough, they simply follow the gas, okay? They rotate around the star together with the gas, okay? The reason why there is this meter-sized barrier problem, one of the reasons, is that when these solid particles stick together and grow enough in size, at some point they get into their size, and then this is again a simplified view, but let's look at the size. When they grow enough in solids, they start to decouple from the gas because they are too big to follow entirely the gas. When they start to do that, they start to interact with the gas in a different way. Okay, they start to go at their own velocity and feel a gas drag. Okay, this is the reason of the gas drag, that then they feel really sucked in through the disk, okay, onto the star. So it is indeed so different sizes of particles do have different velocities because they interact in a different way with the environment. Okay, also the shape matters to some extent. The composition, I would not know, and I don't think it's not one of the main things that would affect the velocity, but the shape also. So in this kind of studies, you start from assuming the simplest conditions, and you assume dust grains that are spheres, just compact spheres with some composition, okay, and some mass. If they grow by sticking of small particles, it's very likely that they are not spheres, but they are fluffier. Okay, so even from lab experiments, we see that when we reach the millimeter, lower size, but when we stick together these particles, they are not a sphere, but they are fluffier. And then, again, that would affect their velocity. Yes? Because
couldn't that account for a particle trap or gas trap?
Maybe in some I would have to think in more details about that.
It sounds like a rolling backup on the beltway.
Classically, you would expect that when you reach a certain size, maybe even assuming the simplified sphere, okay? But when you reach a certain size, you start to decouple from the gas and feed this gas drag. If the shape, fluffier or less fluffy, can matter on this dust trap, I don't know in this detail.
I'd like to thank Dr. Banzatti for his time tonight. Very excellent questions. You're really deep thinkers out here. I forgot to mention at the beginning, there is no observatory tonight. We have clouds and rain. But a lot of stuff to think about, this idea of going from kind of things like spaghetti. Thank you. Hope you enjoyed.
Volunteers with the pasta, please. If you want, you can take it.